Gravity is one of the most familiar yet misunderstood features of the universe humanity lives in. Every moment of every day, gravity quietly shapes motion, guides the paths of planets, and even influences the way time itself flows. Yet most people only meet it through the simplified image of an apple falling on Isaac Newton's head. That popular story is useful as a symbol, but it hides how deep the mystery really goes and how strange the universe becomes when gravity is studied carefully and patiently. Scientists can describe gravity with astonishing precision and can predict its effects across billions of kilometers. Yet when asked what gravity truly is, at its deepest level, the answers suddenly become hesitant and incomplete. The story of Newton and the falling apple captures a turning point in human thinking, but not the full reality of gravity. Newton's great insight was that the same effect that pulls an apple to the ground also holds the moon in orbit around the Earth and keeps the planets moving around the sun. That was a profound unification because it said that the everyday world and the cosmic world are governed by one and the same rule. Newton's mathematics allowed astronomers to predict eclipses, the motions of comets, and even the slow wobble of planetary orbits with impressive accuracy. Yet even Newton admitted that he did not know what mechanism actually carried this invisible pull through apparently empty space. As physics developed, gravity remained the odd one out among the fundamental interactions of nature. In laboratories, electromagnetism, the strong nuclear interaction, and the weak interaction could all be explored in controlled experiments and expressed in the common language of quantum fields and exchange particles. Gravity, by contrast, resisted this treatment. It could be measured and predicted with great precision, yet it could not be placed neatly beside the other forces in a single unified framework. On the largest scales, gravity dominates the architecture of the cosmos, deciding where stars are born, where galaxies form, and how the universe evolves. On the smallest scales of atoms and particles, however, gravity becomes so feeble that it practically disappears. This strange contrast creates one of the deepest puzzles in modern science. At the level of planets, stars and galaxies, gravity behaves as a smooth, continuous field curving the very fabric of space and time. At the level of quantum mechanics, nature seems to work in discrete packets with particles hopping between energy levels and fields fluctuating in tiny quanta. Trying to make these two pictures agree has led to contradictions, paradoxes, and unresolved questions that have challenged theorists for decades. In particular, the search for a consistent theory that treats gravity in the same quantum language as the other interactions remains one of the central unsolved problems in physics. Even the basic characteristics of gravity often defy everyday expectations. Gravity feels weak in ordinary life because human muscles can easily overcome it when a person stands up, jumps, or lifts an object. Yet this apparent weakness is misleading because it comes from comparing gravity only over short distances and small masses. When vast amounts of mass accumulate, such as in planets, stars, and galaxies, the combined gravitational pull becomes powerful enough to shape the large-scale structure of the universe. This dual nature of gravity, being almost negligible in small settings, yet decisive on cosmic scales, makes it both counterintuitive and essential. One of the most astonishing discoveries of modern physics is that gravity influences time itself. According to the general theory of relativity, time does not flow at the same rate everywhere. Where gravity is stronger, time runs more slowly, and where gravity is weaker, time runs more quickly. A clock placed closer to the center of the Earth will tick more slowly than an identical clock located at a higher altitude, even though the difference is tiny for human lifetimes. This means that the idea of one single universal time, shared identically by everyone, is an illusion created by limited experience rather than a fundamental feature of reality. This connection between gravity and time has been confirmed repeatedly by experiments and by practical technologies. Highly precise atomic clocks carried in aircraft or placed on mountains run at slightly different rates compared with clocks kept at sea level, exactly as theory predicts. Navigation systems that depend on satellites must correct for these time differences, otherwise their calculated positions would drift dramatically. These successes show that gravity is not merely a force pulling on objects, but a manifestation of how mass and energy reshape the geometry of space and time. The deeper the investigation goes, the less gravity resembles the simple pull imagined from everyday experience. Because gravity is always present and cannot be shielded, its effects accumulate over immense distances and long periods. Light passing near massive bodies has its path bent, revealing that even massless radiation must follow the curved geometry produced by gravity. Time near extremely dense objects slows down to such an extent that processes which look quick to a local observer can appear frozen to a distant one. In extreme environments like those near black holes, gravity becomes so strong that current theories predict singular behavior, where the usual laws of physics can no longer reliably describe what happens. These situations highlight the limits of present understanding. The strangeness of gravity grows the more closely it is examined. On everyday scales, it behaves steadily and predictably, allowing engineers to design bridges, rockets, and planetary missions with confidence. On cosmic scales, it produces structures of breathtaking complexity, from swirling galaxies to clusters bound together across millions of light years. On quantum scales, however, attempts to apply known rules lead to infinities and contradictions that signal something crucial is missing from current theories. Gravity therefore stands at a crossroads between what is well understood and what remains hidden. For these reasons, gravity often feels almost magical, even though it is studied with the most rigorous scientific tools available. It is familiar enough that a person feels it with every step, yet subtle enough that its true nature continues to elude the brightest minds. It shapes the fate of stars, guides the expansion of the universe, and stretches and squeezes time itself. Despite centuries of work from Newton to Einstein, and beyond, the fundamental question of what gravity really is at the deepest level remains unanswered. Even the most accomplished physicists agree that in many ways humanity still stands at the beginning of understanding this mysterious interaction, and that the journey to uncover its secrets will lead directly into the next parts of this exploration. Gravity began with its strange role as a familiar companion that secretly reshapes space and time, and yet refuses to reveal its true nature. Gravity can slow clocks guide planets and bend light, yet when it is compared with the other fundamental interactions of nature, it behaves in a deeply puzzling way. One of the most striking aspects of this puzzle is that gravity is astonishingly weak when set beside its rivals. This weakness is not a vague impression, but a precise measurable, and it lies at the heart of why gravity is simultaneously easy to feel and hard to study at the deepest level. To understand this weakness, it helps to start with something as ordinary as the human body standing on the surface of the earth. Every person notices the pull of gravity as weight, yet most healthy humans can stand up, jump, or lift objects against that pull, using only the chemical energy stored in muscles. The muscles in a leg or an arm are not especially powerful on a cosmic scale, but they can reliably overcome the combined gravitational attraction of an entire planet beneath their feet. The Earth is an enormous world, and yet a single person can resist its pull for a moment and step forward. This simple experience already hints at the subtle nature of gravity, because it reveals just how feeble the interaction really is per unit of mass. The ordinary impression that gravity is strong comes from the sense that if a person trips, the ground arrives very quickly. That feeling, however, is produced by Earth's sheer size, rather than any intrinsic strength of the gravitational interaction. The Earth has a mass of roughly 5.97 times 10 to the power of 24 kilograms, which is about 5.97 septillion kilograms, a number with 24 zeros after it. This immense quantity of matter gathered into a roughly spherical world creates a gravitational field strong enough to keep the atmosphere bound to the planet, hold the oceans in their basins, and keep the moon circling overhead. Yet, when the same interaction is considered between smaller objects, its true weakness becomes unmistakable. A concrete way to see this weakness is to compare gravity with electromagnetism, using a simple experiment in thought. Suppose a small metal paperclip rests on a table. The entire mass of the Earth pulls downward on that paperclip with all of its gravitational might. Now, bring a modest household magnet close to the clip. The magnetic force from that tiny object is able to lift the paperclip and hold it against gravity. In that moment, the force generated by a bit of aligned electric charge in the magnet defeats the pull of an entire planet. This reveals that on the scale of individual particles and small objects, electromagnetic forces can exceed gravity by staggering odds, while gravity only becomes important when enormous amounts of mass act together. The role of mass accumulation is crucial because gravity, unlike electromagnetism, has no positive and negative versions that can cancel each other out. Electric charges can be positive or negative, and large collections of matter often end up nearly neutral overall, so that their long-range electric forces tend to cancel. Gravity, by contrast, is always attractive, and every bit of mass adds to the total pull. This means that while individual gravitational interactions are extremely feeble, the effect of gathering vast quantities of mass in one place allows gravity to build up gradually until it dominates over other influences on large scales. Stars, planets, and galaxies are held together, not because gravity is strong in itself, but because there is so much mass involved that even a weak attraction becomes decisive. The Earth is a vivid example of this cumulative effect. With its 5.97 septillion kilograms of mass, it generates a surface gravitational acceleration of about 9.8 meters per second squared. That value determines how fast objects fall and how much a person weighs. Yet, this acceleration is the result of adding up the feeble attraction between every particle in the Earth and every particle in the object being pulled. If the Earth were somehow compressed into a smaller radius without changing its mass, the surface gravity would increase because the same total mass would be concentrated closer to the surface. Conversely, if the Earth were puffed up into a much larger sphere with the same mass, the surface gravity would become weaker. This shows that both total mass and distance from the center determine how strongly gravity is felt. It is easy to forget how delicately balanced these effects are because familiarity with Earth's gravity creates an illusion of normality. That a person can stand upright might make gravity seem gentle, while the difficulty of jumping more than a meter high might make it feel harsh. In reality, these impressions say more about the limits of human muscles than about the absolute scale of gravitational strength. To lift a small object, a person must overcome the gravitational force produced by all the matter of the planet. But because that force per kilogram is so small, the task is possible. If gravity were intrinsically much stronger, then even bending a finger might be impossible, and the surface of a planet like Earth would crush ordinary matter. The existence of people walking on the ground is therefore indirect evidence that gravity is weak. Yet the same weak interaction that an individual can resist effortlessly is strong enough on cosmic scales to hold the moon in orbit around the Earth. The moon is not hovering freely in space, but is in continuous free fall under Earth's gravity, following a curved path that never lets it crash into the planet. The pull between Earth and moon raises tides in the oceans, causing the water to bulge toward and away from the moon as our world rotates. These tidal forces not only create the rhythmic rising and falling of sea levels, but also gradually transfer rotational energy from Earth to the moon, slowly increasing the lunar orbital distance over millions of years. Such large-scale consequences arise from the same interaction that allows a person to stand up from a chair. The paradox of gravity can now be stated clearly. On the one hand, gravity is the weakest of the known interactions when measured between individual particles or small objects. On the other hand, that same weak pull shapes the entire visible universe on the largest scales. It gathers diffuse gas into stars, pulls stars into galaxies, and binds galaxies into clusters. Over billions of years, gravity sculpts delicate filaments and vast voids in the distribution of matter, giving the cosmos its large-scale web-like structure. No other interaction manages to act so gently on small scales, yet so dominantly over immense distances. This contrast is not merely philosophical, but central to modern cosmology and astrophysics. If gravity were much stronger relative to other forces, stars might burn out too quickly or collapse before complex structures could form. If it were much weaker, then gas might never condense into stars at all, and the universe would remain a thin mist of particles expanding forever without forming galaxies or planets. The apparent fine balance of gravitational strength compared to the other interactions makes possible a kind of long-lived stable environments in which planets can orbit stars and life can arise. In this sense, the weakness of gravity is not a flaw, but a feature that allows richness and complexity to develop over cosmic time. In summary, gravity is weak when measured locally, yet overwhelmingly influential when considered across the enormous scales of space and time. A human being can win a short contest against the pull of an entire planet, but that same planet can hold a moon and shape its surrounding space. The oceans swell and retreat under the moon's distant tug, while the Earth and Moon together fall around the Sun, guided by the combined gravity of the solar system. From this perspective, gravity appears as a patient sculptor of the universe, working slowly but relentlessly through eons. This strange interaction will be compared more directly with the other fundamental forces of nature to see just how extreme the differences really are, and why gravity remains the most enigmatic of them all. Gravity is surprisingly weak in everyday situations, yet powerful enough to hold the Moon in orbit and shape the large-scale structure of the cosmos. This dual nature raises an important question about how gravity compares with the other fundamental interactions that govern the behavior of matter and energy. Modern physics recognizes 4 fundamental interactions, and gravity is by far the weakest of them when measured in terms of the force between individual particles. Understanding just how extreme this difference is requires a careful look at the other 3 interactions and the roles they play in the structure of matter. The strongest of the fundamental interactions is appropriately named the strong nuclear force. This interaction is responsible for binding together protons and neutrons inside the nuclei of atoms. Without the strong force, atomic nuclei would fly apart instantly because the electromagnetic repulsion between positively charged protons would push them away from each other. The strong force overcomes this repulsion by acting between particles called quarks, which are the building blocks of protons and neutrons. At very short distances on the order of a femtometer, which is about 10 to the power of minus 15 meters, the strong force is enormously powerful. Measurements show that the strong nuclear force is roughly 10 to the power of 38 times stronger than gravity when comparing the interactions between 2 protons at the same distance. This, or of 10 to the power of 38, is almost impossible to grasp intuitively. Written out in full, it is a 1 followed by 38 zeros. To put this in perspective, if gravity were represented by the thickness of a sheet of paper, then the strong force at the same distance would be represented by a stack of paper reaching far beyond the orbit of Neptune. This enormous difference means that gravity is completely negligible when considering what happens inside atomic nuclei. The structure and stability of atoms are determined by the strong and electromagnetic forces, while gravity plays no measurable role at all in nuclear or atomic physics. The second interaction to consider is the weak nuclear force, which, despite its name, is still vastly stronger than gravity. The weak force is responsible for certain kinds of radioactive decay, in which a neutron inside a nucleus transforms into a proton, an electron, and a neutrino, or a proton transforms into a neutron, a positron, and a neutrino. This process is essential for the burning of hydrogen in stars and for the production of many of the elements found in nature. The weak force operates at even shorter ranges than the strong force, and its effects are subtle, but it is still about 10 to the power of 25 times stronger than gravity when comparing particle interactions at similar distances. Even though the weak force is weaker than the strong force and weaker than electromagnetism, it remains orders of magnitude more powerful than gravity. This hierarchy of strengths creates a strange situation in which 3 of the 4 fundamental interactions can be studied and manipulated in laboratories on Earth, while the 4th, namely gravity, can barely be detected between laboratory scale masses. Experiments that probe the strong and weak forces typically involve particle accelerators and detectors that can measure the outcomes of collisions between individual particles. Gravity, by contrast, requires enormous masses or extremely sensitive instruments to reveal its presence at all in controlled settings. The third interaction is electromagnetism, which governs the behavior of electrically charged particles and is responsible for nearly all of the forces experienced in daily life, apart from gravity itself. When a person pushes on a table, the resistance comes from electromagnetic forces between the atoms in the hand and the atoms in the table. The rigidity of solid objects, the flow of electric currents, the emission and absorption of light, and the chemistry that makes life possible are all expressions of electromagnetism. The electromagnetic force between two protons at a given distance is about 10 to the power of 36 times stronger than the gravitational force between them. This is nearly as extreme as the comparison with the strong force. The dominance of electromagnetism in everyday experience often hides the true weakness of gravity. A person turning on a light switch is manipulating electromagnetic forces that move electrons through wires and cause atoms in a filament or a diode to emit photons. The energy released by chemical reactions in batteries or in metabolic processes comes from changes in electromagnetic bonds between atoms. Even the sensation of touch or the resistance felt when bending a metal rod arises from electromagnetic interactions. Gravity contributes to weight and determines which way is down, but almost everything else about daily experience is electromagnetic in origin. This shows that nature has organized itself so that electromagnetism and the nuclear forces control small-scale structure, while gravity waits patiently to act on larger scales. Despite being the weakest interaction, gravity has one unique property that allows it to dominate on cosmic scales. Unlike the other forces, gravity acts on all forms of mass and energy without exception, and it is always attractive. The strong force only acts over distances comparable to the size of a nucleus and becomes negligible beyond that range. The weak force has an even shorter reach. Electromagnetism has infinite range like gravity, but electric charges come in positive and negative varieties, which tend to cancel each other out in large neutral objects. Gravity, by contrast, never cancels. Every bit of mass attracts every other bit, and there is no such thing as negative mass to provide a repulsive counterpart. This means that even though gravity is incredibly feeble per particle, its effects add up coherently when large amounts of matter are gathered together. This cumulative property of gravity explains why it is irrelevant inside atoms but essential for stars, planets and galaxies. A single proton and electron in a hydrogen atom are bound together by electromagnetism, and the gravitational attraction between them is so small that it can be ignored entirely without affecting any predictions. However, when trillions upon trillions of hydrogen atoms gather together into a cloud in space, the combined gravitational pull of all that mass begins to compress the cloud. As the cloud contracts, it heats up, and eventually the core becomes hot and dense enough for nuclear fusion to ignite. At that moment, a star is born, and its entire life cycle from birth to death is governed by the interplay between gravity pulling inward and pressure pushing outward. The same principle applies to the formation of planets, moons, asteroids, and every other large-scale structure in the universe. Gravity is the architect that gathers raw materials and arranges them into organized systems. It pulls together the gas and dust in a protoplanetary disk and allows solid bodies to grow through collisions and accretion. Once a planet forms, gravity holds its atmosphere in place, shapes its interior through pressure and heat, and determines whether it can retain liquid water on its surface. On even larger scales, gravity binds stars into galaxies, and galaxies into clusters, creating the vast cosmic web that stretches across hundreds of millions of light years. Therefore, while gravity is the weakest force by a staggering margin when measured between individual particles, it is the only force that can act persistently and cumulatively across the entire universe. The strong force binds quarks and nucleons, but it does not reach beyond the nucleus. The weak force enables certain decay processes, but it does not build structures. Electromagnetism shapes atoms, molecules, and the behavior of charged particles, but large objects tend to be electrically neutral, and so electromagnetic forces do not dominate on planetary or galactic scales. Gravity alone is both universal in its reach and relentless in its action. It is slow, but it never stops, and over billions of years it shapes the cosmos into the form observed today. This contrast between the weakness of gravity and its cosmic importance creates one of the central mysteries in modern physics. Why is gravity so much weaker than the other interactions? And why does nature permit such an enormous hierarchy of strengths? Some theories suggest that gravity might actually be comparable in strength to the other forces, but that its influence is diluted by spreading into extra dimensions of space that remain hidden from ordinary experience. Other ideas propose that the apparent weakness is a clue to new physics that will only be revealed at energies far beyond the reach of current experiments. These questions remain open and are among the most actively debated topics in theoretical physics today. In summary, gravity is tens of orders of magnitude weaker than the strong nuclear force, the weak nuclear force, and electromagnetism. Yet it is the force that ultimately determines the fate of stars, planets, and galaxies. Its unique properties of infinite range, universal coupling, and purely attractive character allow it to dominate over vast distances, despite being negligible at small scales. This strange behavior will be explored further by examining the infinite reach of gravity and how even distant objects continue to pull on each other across the immense voids of space. Gravity has an effectively infinite range, connecting every mass in the universe to every other mass through an invisible web of attraction that respects the speed of light and shapes the large-scale structure of the cosmos. This universal reach already makes gravity unlike any other interaction, but there is an even stranger consequence of gravitational influence that defies everyday intuition. Gravity does not merely pull on objects and curve their paths through space, it also affects the flow of time itself. According to Einstein's general theory of relativity, time does not pass at the same rate everywhere. Where gravity is stronger, time runs more slowly, and where gravity is weaker, time runs more quickly. This effect is called gravitational time dilation, and it has been confirmed through countless experiments and observations. The idea that time could be flexible rather than absolute was one of the most revolutionary insights of 20th century physics. Before Einstein, most scientists assumed that time was a universal backdrop against which events unfolded, and that clocks everywhere would tick at the same rate if they were properly synchronized. Einstein showed that this assumption was wrong. Time is not independent of space or matter. Instead, time and space are woven together into a single structure called space-time, and the presence of mass and energy warps this structure in ways that affect both the paths of objects and the rate at which time passes. To understand how gravity affects time, it helps to consider a concrete example. Imagine two identical clocks, one placed at sea level on the surface of Earth and the other placed on top of a high mountain. The clock at sea level is deeper in Earth's gravitational field because it is closer to the center of the planet. The clock on the mountain is at a higher altitude and therefore experiences slightly weaker gravity. According to general relativity, the clock at sea level will tick more slowly than the clock on the mountain. The difference is extremely small, only a few billionths of a second per day, but it is real and measurable with precise instruments. This prediction has been tested many times using atomic clocks, which are among the most accurate timekeeping devices ever built. In one famous experiment conducted in the early 1970s, physicists placed atomic clocks on commercial airplanes and flew them around the world. When the clocks returned, they were compared with identical clocks that had remained on the ground. The traveling clocks showed a tiny but measurable difference in elapsed time, exactly as predicted by relativity. Part of this difference was due to the motion of the airplane, which causes another effect called velocity time dilation, but part was due to the change in gravitational strength at higher altitude. The results confirmed that time truly does flow at different rates, depending on position in a gravitational field. The implication of this discovery is profound. It means that there is no such thing as a single universal time shared by everyone. Every person experiences time at a slightly different rate depending on where they are and how they are moving. Someone standing on the ground floor of a tall building ages slightly more slowly than someone standing on the top floor because the ground floor is deeper in Earth's gravitational field. The difference is far too small to notice in a human lifetime, amounting to only a tiny fraction of a second over many years, but it is a real physical effect, not just a mathematical curiosity. The effect becomes more dramatic in stronger gravitational fields. Near the surface of a neutron star, where gravity is millions of times stronger than on Earth, time dilation becomes extreme. A clock on the surface of such a star would tick noticeably slower than a clock far away in weak gravity. An observer watching from a safe distance would see events on the neutron star surface unfolding in slow motion. Conversely, an observer on the neutron star surface looking outward would see distant events happening much faster. Both perspectives are valid, but they experience time differently because they occupy different positions in the curved space-time around the massive object. Even more remarkable is that this time dilation applies not only to clocks, but to all physical processes. Radioactive decay, the vibrations of atoms, the firing of neurons in a brain, and the beating of a heart all happen more slowly in stronger gravity. Time itself is not just a label attached to events, but a fundamental aspect of physical reality that is shaped by the distribution of mass and energy. This challenges the common sense notion that time is something external and unchanging. Instead, time is part of the dynamic fabric of the universe, and it responds to the presence of matter just as space does. One of the most striking consequences of gravitational time dilation concerns the Earth itself. The center of the Earth is about 6,000 kilometers below the surface, and therefore deeper in the planet's gravitational field. This means that time passes more slowly at the core than at the surface. Over the billions of years since Earth formed, this difference has accumulated. Calculations show that the core of the Earth is roughly 2.5 years younger than the surface in terms of elapsed proper time. This does not mean that the core formed later, but rather that clocks running at the core would have ticked fewer times than clocks at the surface over the same period of cosmic history. This result is not just a theoretical oddity. It reflects that the Earth is not a rigid, unchanging object, but a dynamic system where different parts experience time at different rates. The rocks at the center have aged slightly less than the rocks at the surface, even though they formed at the same moment. This idea can be disorienting because it contradicts the intuitive picture of time as a uniform flow, but it is a direct consequence of the way gravity warps space-time. The Earth and every other massive object exists in a gravitational field that is stronger in some places and weaker in others, and this variation creates a corresponding variation in the rate of time. The realization that time is not uniform has practical consequences for technologies that depend on precise timing. Satellite navigation systems, such as the Global Positioning System, known as GPS, rely on signals sent from satellites orbiting high above Earth. These satellites carry atomic clocks that must be synchronized with clocks on the ground to provide accurate location data. However, the satellites experience weaker gravity than clocks at Earth's surface because they orbit at altitudes of about 20,000 kilometers. This means that time passes slightly faster on the satellites than on the ground. If this effect were not corrected, the navigation system would accumulate errors and the calculated positions would drift by several kilometers per day. Engineers who designed the GPS system had to account for both gravitational time dilation and velocity time dilation. The satellites are moving at high speeds, which causes their clocks to run slower due to special relativity, but they are also higher in the gravitational field, which causes their clocks to run faster due to general relativity. The two effects partially cancel, but they do not cancel completely. The net result is that satellite clocks gain about 38 microseconds per day compared to clocks on the ground. This tiny discrepancy must be corrected in software, otherwise the system would quickly become useless. Every time a person uses a navigation app on a phone, they are relying on corrections based on Einstein's theory of gravity, and that time flows at different rates in different places. The flexibility of time under the influence of gravity also means that the concept of simultaneity becomes ambiguous. Two events that appear to happen at the same time, according to one observer, may not be simultaneous according to another observer in a different gravitational field or moving at a different speed. This relativity of simultaneity is one of the key insights of Einstein work, and it shows that the universe does not have a single objective present moment. Instead, the structure of space-time allows different observers to slice time and space in different ways, all of which are equally valid within their own reference frames. Gravitational time dilation also provides a window into the nature of reality itself. It shows that time is not a separate entity that exists independently of matter and space, but rather an inseparable part of the geometry of the universe. The presence of mass curves, space-time, and this curvature affects both the motion of objects and the passage of time. That time can be stretched or compressed depending on gravitational strength, suggests that time is a physical phenomenon subject to the same kinds of laws and influences as energy, momentum, and force. In everyday life, these effects are so small that they go unnoticed. A person living on the ground floor of a building does not feel younger than someone on the top floor, and no one senses the tiny variations in time flow caused by changes in altitude or motion. Yet the effects are always present, and they become significant whenever high precision is required, or when extreme gravitational fields are involved. The universe is filled with places where gravity is strong enough to produce dramatic time dilation, from the surfaces of white dwarfs and neutron stars to the regions near black holes where time distortion becomes so extreme that the usual rules of physics begin to break down. In summary, gravity does not only pull on matter, but also warps the flow of time, causing clocks in stronger gravitational fields to tick more slowly than clocks in weaker fields. This effect has been confirmed through experiments with atomic clocks flown on airplanes and satellites, and it is essential for the accurate functioning of modern navigation systems. The Earth core is younger than its surface by about 2.5 years, due to the accumulated effects of time dilation over billions of years. These reveal that time is not a fixed universal backdrop, but a flexible dimension of reality shaped by the presence of mass and energy. The interplay between gravity and velocity will be explored, showing how both effects compete to influence the passage of time, and how these principles are tested in real-world situations such as the orbits of astronauts aboard the International Space Station. Gravity warps the flow of time itself, causing clocks in stronger gravitational fields to run slower than those in weaker fields, and showing that the Earth core is actually younger than its surface by roughly 2.5 years. This gravitational time dilation is not the only way that time can be affected. According to Einstein's special theory of relativity motion, also influences the passage of time. An object moving at high speed experiences time more slowly than an object at rest. This effect is called velocity time dilation, and it occurs independently of gravity. When both effects are present, they compete with each other, creating a fascinating interplay that can be observed and measured in real situations. Velocity time dilation arises from the structure of space-time itself, and it becomes significant when objects move at speeds approaching the speed of light. For everyday speeds, such as walking or driving, the effect is utterly negligible. However, for objects moving at thousands of kilometers per second, the difference becomes measurable. The faster an object moves relative to an observer, the slower its clock appears to tick from that observer perspective. This is not an illusion caused by delays in signal transmission, but a real physical difference in the passage of time. A moving clock literally experiences less time than a stationary clock over the same interval as measured in the reference frame of the stationary observer. This prediction of special relativity has been tested in many experiments. One of the most famous involves particles called muons, which are created when cosmic rays strike the upper atmosphere. Muons are unstable and decay into other particles with a half-life of only about 2 microseconds when measured at rest. Given their speed and this short lifetime, most muons created high in the atmosphere should decay before reaching the ground. However, detectors at sea level observe far more muons than expected. The reason is that the muons are moving at speeds close to the speed of light, and from the perspective of an observer on the ground, their internal clocks run slowly. This time dilation allows them to survive long enough to reach the surface. The effect has been measured precisely, and it agrees perfectly with the predictions of special relativity. When an object is both moving and located in a gravitational field, both velocity-time dilation and gravitational time dilation occur simultaneously. The total time dilation is the combination of these two effects. In some situations, they work in opposite directions. For example, an object moving quickly in a weak gravitational field might experience slower time due to its motion, but faster time due to the reduced gravity, compared to a stationary object deeper in a gravitational well. The net result depends on the relative strengths of the two effects. Calculating the combined outcome requires careful application of both special and general relativity. A perfect example of this interplay can be found by studying astronauts aboard the International Space Station, which orbits Earth at an altitude of roughly 400 kilometers. The space station travels at a speed of about 28,000 kilometers per hour, or roughly 7.7 kilometers per second. This high velocity causes time dilation according to special relativity. From the perspective of observers on the ground, the clocks aboard the space station should tick more slowly due to the motion of the station. However, the space station is also higher in Earth gravitational field than observers on the surface. This means that gravitational time dilation causes clocks on the station to tick faster compared to clocks on the ground. These two effects work against each other, and the question becomes which one dominates. Detailed calculations show that for the International Space Station, the velocity effect is stronger than the gravitational effect. The result is that astronauts aboard the station experience time slightly more slowly than people on Earth. Over the course of a typical 6-month mission, an astronaut loses about 7 milliseconds compared to clocks on the ground. This is an extremely small amount, only 7/1000ths of a second, but it has been confirmed through precise measurements of atomic clocks carried on the station and compared with reference clocks on Earth. This tiny difference in elapsed time may seem trivial, but it provides a powerful confirmation of both special and general relativity operating together in a real, measurable system. The astronauts are not simply moving through space, but are also navigating the curved space-time created by Earth mass. Both the curvature of space-time and the motion through it contribute to the way time passes. That scientists can predict the exact amount of time dilation and then verify it with experiments demonstrates the accuracy and consistency of Einstein theories. The competing effects of gravity and velocity also have important implications for understanding the universe on larger scales. Stars orbiting near the centers of galaxies move at very high speeds, but they are also deep in the gravitational wells created by the concentrated mass of stars and dark matter in the galactic core. Both effects alter the passage of time for those stars compared to stars in the outer regions of the galaxy, where gravity is weaker and orbital speeds are lower. Over billions of years, these differences accumulate and affect the evolution of stellar systems and the distribution of matter in galaxies. Another striking example occurs in binary star systems, where two stars orbit each other closely. If one of the stars is a compact object such as a white dwarf or a neutron star, the gravitational field near its surface is extremely strong. Time dilation near such an object can be significant. Meanwhile, the orbital motion of both stars contributes velocity-time dilation. Astronomers studying these systems must account for both effects when interpreting observations of light emitted by the stars. The wavelengths of spectral lines can be shifted not only by the motion of the stars, but also by the gravitational time dilation near the compact object. These shifts provide clues about the masses and sizes of the stars and help test the predictions of general relativity in strong field environments. The combination of gravitational and velocity time dilation also plays a role in the behavior of light itself. Photons traveling through a gravitational field experience a change in energy, which manifests as a shift in frequency and wavelength. Light climbing out of a gravitational well loses energy and becomes redshifted, meaning its wavelength increases and its frequency decreases. Light falling into a gravitational well gains energy and becomes blue shifted. This gravitational redshift is a direct consequence of time dilation because the frequency of light is related to the rate at which oscillations occur, and that rate depends on the flow of time at the location where the light is emitted. Gravitational redshift has been measured in laboratory experiments on Earth and observed in the light from white dwarfs and neutron stars. One of the earliest tests was conducted in 1959 by physicists Robert Pound and Glenn Rebka, who measured the shift in frequency of gamma rays traveling vertically in a tower at Harvard University. Even over a height difference of only about 22 meters, the change in gravitational potential was enough to produce a measurable redshift. The experiment confirmed that light is affected by gravity in exactly the way predicted by general relativity. This result provided further evidence that gravity is not simply a force acting on massive objects, but a curvature of space-time that affects all forms of energy, including light. The interplay between gravity and velocity becomes even more dramatic near extremely compact objects, such as black holes. Far from a black hole where gravity is weak, an orbiting object might experience only mild time dilation. Closer to the event horizon where gravity becomes intense, both gravitational time dilation and the high orbital speeds required to avoid falling in combine to produce extreme distortions of time. An observer far away watching an object fall toward a black hole would see the object appear to slow down as it approaches the event horizon, and its clock would seem to tick more and more slowly. From the perspective of the infalling object, however, time would continue to pass normally, and it would cross the horizon in a finite amount of proper time. This difference in perspectives illustrates the profound relativity of time in curved space-time. These effects are not merely theoretical curiosities, but have practical consequences for any technology or observation that requires precise timing. In addition to satellite navigation systems, astronomers measuring the properties of distant objects must account for time dilation, caused by both the motion of those objects and the gravitational fields they inhabit. Pulsar timing arrays, which use the incredibly regular pulses of rotating neutron stars, as cosmic clocks must correct for time dilation effects to achieve the precision needed to detect gravitational waves and other subtle phenomena. Even the operation of particle accelerators on Earth, where particles are accelerated to nearly the speed of light, requires understanding of velocity time dilation to predict the lifetimes of unstable particles. The time dilation accumulates over long periods, means that even tiny differences in the rate of time flow can add up to significant amounts. An astronaut spending 6 months aboard the International Space Station loses only 7 milliseconds, but if missions lasted years, the differences would grow proportionally. Similarly, the gravitational time dilation experienced at different altitudes on Earth is small per day, but over centuries or millennia it could become noticeable if precise records were kept. This accumulation is important for understanding geological processes, cosmic evolution, and the history of the universe, where time scales span millions or billions of years. In summary, velocity time dilation caused by motion and gravitational time dilation caused by the curvature of space-time are two distinct effects that often occur together and can either reinforce or oppose each other. Astronauts aboard the International Space Station lose about 7 milliseconds over 6 months because their high orbital speed causes more time dilation than the reduced gravity at their altitude can compensate for. These effects confirm the predictions of both special and general relativity, and they are essential for the accurate functioning of modern technologies, such as navigation systems and astronomical observations. The competition between gravity and velocity in shaping the flow of time reveals the deep interconnection between motion mass and the structure of space-time. The focus will shift to one of the most important practical applications of these principles, namely the global positioning system, and how corrections for both gravitational and velocity time dilation are essential to its operation. How velocity time dilation and gravitational time dilation can work together or against each other depending on the circumstances, and showed that astronauts aboard the International Space Station experience time slightly more slowly due to the combined effects of their high orbital speed and their position in Earth's gravitational field. These time dilation effects are not just abstract features of theoretical physics, but have direct practical consequences for technologies that require extreme precision in timekeeping. One of the most important and widely used systems that depends on accurate treatment of both gravitational and velocity time dilation is the Global Positioning System, which provides navigation and location data to billions of people every day. The Global Positioning System consists of a network of satellites orbiting Earth at altitudes of roughly 20,000 kilometers above the surface. Each satellite carries highly accurate atomic clocks that broadcast time-stamped signals. A receiver on the ground, such as a smartphone or a navigation device, picks up signals from multiple satellites and uses the timing information to calculate its own position. The basic principle is simple. By measuring how long it takes for signals to travel from several satellites to the receiver, the system can determine the distances to those satellites and use geometry to pinpoint the receiver location on Earth. However, this process requires that the clocks on the satellites and the clocks in the receivers are synchronized to an extraordinary degree. If the satellite clocks were not properly synchronized with ground-based clocks, the calculated distances would be incorrect, and the position data would rapidly drift into error. Because the signals travel at the speed of light, which is about 300,000 kilometers per second, even a tiny error in timing translates into a large error in position. The observed time dilation matches the theoretical predictions to a high degree of precision. Any significant deviation from the expected values would indicate a problem with the theory or with the implementation of the corrections. So far, no such deviations have been found. This ongoing agreement between theory and observation strengthens confidence in the validity of general relativity and demonstrates that the theory correctly described the behavior of clocks in varying gravitational fields and at different velocities. Beyond navigation satellites, time dilation effects are also important for other space-based technologies. Communication satellites orbiting at different altitudes experience different amounts of time dilation. Earth observation satellites that need to coordinate their data with ground-based measurements must account for that time passes at slightly different rates in orbit. Even crewed space missions must consider these effects when synchronizing activities between astronauts in orbit and mission control on the ground. Although the time differences are small, they can accumulate over the duration of a mission and must be taken into account for precise scheduling and data correlation. The importance of time dilation corrections extends to fundamental physics research as well. Experiments that use satellites to test the principles of quantum mechanics or to search for violations of fundamental symmetries often require extremely precise timing. Any experiment that compares measurements made at different locations or different altitudes must account for gravitational time dilation. Similarly, experiments involving fast-moving particles or high-energy processes must consider velocity time dilation. The ability to make these corrections accurately is essential for achieving the sensitivity needed to detect subtle effects and to push the boundaries of scientific knowledge. The Global Positioning System also serves as an educational tool. It provides a concrete example of how relativity affects the real world in a way that is accessible to a wide audience. Students learning about time dilation can point to the navigation system as proof that these effects are not just theoretical abstractions, but practical realities that must be managed in everyday technology. This connection between fundamental physics and practical application helps to make the concept of relativity more tangible and understandable. It shows that science is not just about understanding the universe in the abstract, but also about building tools and systems that improve human life. In summary, the Global Positioning System relies on a network of satellites orbiting at roughly 20,000 kilometers altitude and traveling at speeds of about 22,000 kilometers per hour. These satellites experience both gravitational time dilation, which causes their clocks to gain about 45 microseconds per day, and velocity time dilation, which causes their clocks to lose about 7 microseconds per day. The net effect is that satellite clocks run fast by about 38 microseconds per day compared to ground-based clocks. Without corrections for these relativistic effects, the system would accumulate position errors of roughly 10 kilometers per day, making it useless for accurate navigation. Engineers compensate for this by programming the satellite clocks to tick at a slightly slower rate, so that once in orbit they remain synchronized with clocks on Earth. The success of this system confirms the predictions of Einstein theories of special and general relativity and demonstrates that the flow of time is truly influenced by both gravity and motion. The discussion will move beyond the practical applications of time dilation to explore the deeper nature of gravity itself, revealing that gravity may not be a force in the traditional sense, but rather a manifestation of the curvature of space-time. Gravity is not a force in the traditional sense, but rather a curvature of space-time itself, with mass and energy warping the geometry through which all objects and signals travel along paths called geodesics. This geometric view of gravity leads to one of the most striking and counterintuitive predictions of general relativity, which is that light itself can be bent by gravity, even though light has no mass. In the Newtonian picture, gravity acts on mass, and a massless particle like a photon should not be affected. However, in Einstein's framework, light follows the curvature of spacetime, just as any material object does, and this means that the path of light can be deflected when it passes near a massive body. The bending of light by gravity was one of the first tests of general relativity, and its confirmation provided powerful evidence that Einstein's theory was correct. In 1915, Einstein calculated that light from a distant star passing near the edge of the sun should be deflected by a small but measurable angle. The prediction was about 1.75 arc seconds, which is less than 1,000th of a degree, but still detectable with careful astronomical observations. The challenge was that stars near the sun are not normally visible because the sun glare overwhelms their faint light. The only time such observations could be made was during a total solar eclipse, when the moon blocks the sun direct light and allows stars near the solar limb to be seen. The opportunity came in May of 1919, when a total solar eclipse occurred under favourable conditions. 2 expeditions were organised, one led by British astronomer Arthur Eddington to the island of Príncipe off the coast of West Africa, and another to Sobral in Brazil. Both teams photographed stars near the sun during the eclipse, and then compared their positions with photographs of the same region of the sky taken at night when the sun was not present. The comparison showed that the stars appeared to be shifted slightly outward from their usual positions, exactly as Einstein had predicted. The measured deflection agreed with the prediction of general relativity, and disagreed with the smaller deflection that would have been expected from a naive application of Newtonian gravity to light treated as if it had a tiny mass. This result was announced publicly in November of 1919, and it made Einstein an international celebrity overnight. Newspapers around the world proclaimed that the fabric of space itself had been shown to be curved, and that a new understanding of the universe had been achieved. The success of the eclipse observations demonstrated that light is indeed affected by gravity, and that the curvature of space-time is a real physical phenomenon, not just a mathematical abstraction. Since that time, the bending of light by gravity has been observed in countless situations, and it has become one of the most important tools in modern astronomy. The effect of gravity on light is now known as gravitational lensing, because massive objects act like lenses, bending and focusing light from more distant sources. Just as a glass lens can bend light rays and create magnified or distorted images, a massive object in space can bend the light from a background object and alter the way that object appears to an observer. Gravitational lensing can take several forms depending on the alignment and the masses involved. When the alignment is nearly perfect and the lensing mass is very large, the result can be a spectacular ring of light surrounding the lensing object. This is called an Einstein ring, and it occurs when the light from a distant source is bent equally in all directions around the lens, creating a circle of light. More commonly, the alignment is not perfect and the result is multiple distorted images of the background object or elongated arcs of light. Astronomers have observed many examples of such lensing in which a distant galaxy appears as several separate images scattered around a foreground galaxy or cluster. By studying the positions and shapes of these images, astronomers can infer the distribution of mass in the lensing object. This is particularly valuable for studying dark matter, which does not emit or absorb light, but still curves space-time. Gravitational lensing provides a direct way to map where dark matter is located and how much of it is present, even though it cannot be seen directly. One of the most famous examples of gravitational lensing was discovered in the early 1980s when astronomers found what appeared to be two nearly identical quasars very close together in the sky. Quasars are extremely bright and distant objects, powered by supermassive black holes at the centers of galaxies. It seemed unlikely that two such similar objects would be so close to each other by chance. Further investigation revealed that the two images were actually a single quasar whose light had been split into two by a massive galaxy lying between the quasar and Earth. This was the first confirmed case of a multiply-image distant object, and it provided clear evidence that gravitational lensing was a real and observable phenomenon. Since then, thousands of gravitational lensing events have been catalogued. Some involve strong lensing where the distortion is dramatic and produces multiple images or arcs. Others involve weak lensing where the distortion is subtle and can only be detected statistically by analyzing the shapes of many background galaxies. Weak lensing has become a powerful tool for studying the large-scale structure of the universe and for measuring the total amount of matter, including dark matter, in large regions of space. By observing how the light from distant galaxies is slightly distorted by the gravitational influence of foreground structures, astronomers can create maps of the matter distribution across vast areas of the sky. Gravitational lensing also allows astronomers to study objects that would otherwise be too faint or too distant to observe. When a massive object acts as a lens, it can magnify the light from a background source, making it appear brighter and larger. This natural magnification has been used to study some of the most distant galaxies in the universe, which formed only a few 100 million years after the Big Bang. Without the magnification provided by intervening clusters of galaxies, these distant objects would be far too faint to detect, even with the most powerful telescopes. Gravitational lensing therefore serves as a cosmic telescope, extending the reach of human observation far beyond what would otherwise be possible. The bending of light by gravity also provides a way to test the predictions of general relativity in strong gravitational fields. For example, the light emitted from the surface of a neutron star or from the accretion disk around a black hole must travel through regions of intense space-time curvature. The paths of the photons are strongly bent, and this affects the spectrum and appearance of the emitted light. By comparing observations with detailed models based on general relativity, astronomers can test whether the theory accurately describes the behavior of light in these extreme environments. So far, all such tests have confirmed the predictions of general relativity with high precision. Another remarkable consequence of the interaction between light and gravity is the phenomenon of gravitational redshift, which was discussed earlier in the context of time dilation. Light climbing out of a gravitational well loses energy and its wavelength increases. This redshift is a direct result of that time runs more slowly deeper in a gravitational field. A photon emitted at a lower gravitational potential where time is slower will appear to have a lower frequency and longer wavelength when observed at a higher potential where time is faster. This effect has been measured in laboratory experiments and observed in the light from white dwarfs and other compact objects. It provides yet another confirmation that gravity affects not only the motion of particles, but also the propagation of light. Gravitational lensing and the bending of light also play a role in the study of exoplanets, which are planets orbiting stars other than the Sun. A technique called gravitational microlensing takes advantage of that when a foreground star passes in front of a more distant background star, the gravity of the foreground star can briefly magnify the light from the background star. If the foreground star has a planet orbiting it, the planet gravity can produce an additional small spike in the brightness. By monitoring these events, astronomers have discovered dozens of exoplanets, including some that are too far from their host stars to be detected by other methods. This demonstrates that gravitational lensing is not only a tool for studying galaxies and dark matter, but also for finding new worlds. Light follows curved space-time means that gravity is truly universal in its influence. It affects everything that moves through space-time, whether it has mass or not. This universality is one of the defining features of gravity, and it sets gravity apart from the other fundamental interactions. Electromagnetism acts only on charged particles. The strong and weak nuclear forces act only on specific types of particles at very short ranges. Gravity acts on all forms of energy and momentum without exception, and it does so by shaping the very geometry through which those forms of energy and momentum propagate. This makes gravity unique, and it explains why gravity is so important on cosmic scales, even though it is the weakest of the fundamental interactions. The discovery that light is affected by gravity and the development of gravitational lensing as an observational tool have transformed astronomy over the past century. What began as a bold theoretical prediction tested during a solar eclipse has become a routine technique used to map the universe, measure distances, study dark matter, and discover new objects. The bending of light by space-time curvature is no longer a curiosity but a fundamental part of how astronomers understand and explore the cosmos. It provides a direct window into the nature of gravity and the geometry of space-time, showing that Einstein's vision of a curved universe is not only correct, but also profoundly useful. The story will turn to the most extreme manifestations of space-time curvature, namely black holes where gravity becomes so strong that not even light can escape, and where the predictions of general relativity are pushed to their absolute limits. Light, despite having no mass, is bent by the curvature of space-time, and that this gravitational lensing has become an essential tool for mapping the universe detecting dark matter, and studying distant objects. The bending of light shows that gravity truly affects everything that moves through space-time. But there are regions in the cosmos where gravity becomes so intense that even light cannot escape. These regions are called black holes, and they represent the most extreme manifestations of space-time curvature that nature is known to produce. Black holes are places where the predictions of general relativity are pushed to their absolute limits, and where the familiar laws of physics begin to break down in ways that are both fascinating and deeply mysterious. A black hole forms when a large amount of mass is compressed into an extraordinarily small volume, creating a gravitational field so strong that the escape velocity exceeds the speed of light. The boundary surrounding this region is called the event horizon. Anything that crosses the event horizon, whether matter or light, is trapped forever and cannot return to the outside universe. From the perspective of an outside observer, the event horizon is a one-way surface. Light signals and particles can fall in, but nothing can come out. This makes the interior of a black hole completely hidden from external observation, and it gives black holes their name because they appear utterly black against the background of space. The concept of an object so dense that light could not escape was speculated about even before Einstein developed general relativity. In the late 18th century, the English natural philosopher John Michel and the French mathematician Pierre-Simon Laplace independently considered the possibility that a sufficiently massive and compact body could have an escape velocity greater than the speed of light. However, these early ideas were based on Newtonian gravity and treated light as if it were made of particles with mass. The modern understanding of black holes only became possible after Einstein published his field equations in 1915. Within months, the German physicist Karl Schwarzschild found an exact solution to these equations, describing the space-time around a spherical, non-rotating mass. This solution predicted the existence of an event horizon at a specific radius, now called the Schwarzschild radius. For many years, black holes were regarded as purely theoretical objects, and many physicists, including Einstein himself, doubted whether they could actually exist in nature. The conditions required to form a black hole seemed too extreme. However, advances in the understanding of stellar evolution in the mid-20th century showed that black holes could form naturally as the end products of the lives of very massive stars. When a star much more massive than the Sun exhausts its nuclear fuel, it can no longer generate the pressure needed to support itself against gravity. The core collapses catastrophically, and if the core mass is large enough, no known force can stop the collapse. The result is a black hole. The first strong evidence for the existence of black holes came in the 1970s when astronomers discovered powerful X-ray sources in binary star systems. In these systems, a visible star orbits an invisible companion that pulls gas from the star surface. As the gas spirals inward toward the compact object, it heats up to millions of degrees and emits X-rays. By studying the motion of the visible star, astronomers could estimate the mass of the unseen companion. In some cases, the mass was far too large to be a neutron star, which is the other possible remnant of a massive star. The only plausible explanation was that the companion was a black hole. Since then, many such systems have been identified, and the existence of stellar mass black holes is now firmly established. In addition to stellar mass black holes, which typically have masses between a few and a few dozen times the mass of the Sun, there are supermassive black holes with masses millions or even billions of times that of the Sun. These giants reside at the centers of most large galaxies, including the Milky Way. The supermassive black hole at the center of our galaxy, known as Sagittarius A star, has a mass of about 4 million solar masses. Astronomers have tracked the orbits of stars near this black hole and observed that they move at tremendous speeds, following paths determined by the intense gravitational field. The motions of these stars provide some of the most convincing evidence that a supermassive black hole is present. The event horizon of a black hole is not a physical surface, but rather a boundary in space-time. There is no wall or barrier at the horizon. An object falling toward a black hole would cross the event horizon without experiencing any sudden change or collision. From the perspective of the infalling object, the passage through the horizon happens in a finite amount of proper time, and nothing unusual is felt at that moment. However, from the perspective of an outside observer watching the object fall, the situation looks very different. As the object approaches the horizon, it appears to slow down, and its light becomes increasingly redshifted. The outside observer never actually sees the object cross the horizon. Instead, the object appears to freeze just above the horizon and fade from view as its light is stretched to longer and longer wavelengths. This difference in perspectives is a consequence of the extreme time dilation near the event horizon. Time runs infinitely slowly at the horizon, as measured by a distant observer. This means that events occurring at or near the horizon take an infinitely long time to unfold from the outside perspective. However, for the infalling observer, time continues to pass normally, and the horizon is crossed in a finite time. This contrast illustrates the profound relativity of time in curved space-time, and it shows that different observers can have very different experiences of the same events depending on their location and motion. Once inside the event horizon, an object is doomed. All possible future paths through space-time lead toward the center of the black hole, where general relativity predicts the existence of a singularity. A singularity is a point or region where the curvature of space-time becomes infinite and where the known laws of physics break down. At the singularity, densities and gravitational forces become infinite, and the equations of general relativity no longer provide meaningful predictions. The existence of singularities is one of the major unsolved problems in theoretical physics because it signals that the theory is incomplete. Most physicists believe that a complete theory of quantum gravity will resolve the singularities and provide a consistent description of what happens at the center of a black hole. But such a theory has not yet been developed. The interior of a black hole is hidden behind the event horizon, and no information can escape from within. This means that the details of what happens inside are fundamentally inaccessible to outside observers. The only properties of a black hole that can be measured from the outside are its mass, its electric charge, and its angular momentum. According to a theorem in general relativity known as the no-hair theorem, these three quantities completely determine the external gravitational and electromagnetic fields of a black hole. All other information about the matter that formed the black hole or fell into it is lost. This loss of information has led to deep questions about the nature of information and entropy in quantum mechanics, and it remains an active area of research. Black holes also exhibit remarkable effects on their surroundings. The intense gravity near a black hole can accelerate particles to extremely high energies and generate powerful jets of matter and radiation. Supermassive black holes at the centers of galaxies are thought to be responsible for some of the most energetic phenomena in the universe, including quasars and active galactic nuclei. These objects can outshine entire galaxies, and their influence extends across vast distances, affecting the formation and evolution of stars and the distribution of gas in their host galaxies. Black holes are therefore not just passive objects, but active players in the cosmic drama. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. The image showed the shadow of the supermassive black hole at the center of the galaxy Messier 87, surrounded by a bright ring of glowing gas. The shadow is the region where light rays are captured by the black hole and cannot reach the observer. The bright ring is produced by light emitted from the hot gas, orbiting just outside the event horizon. This image provided striking visual confirmation of the existence of black holes, and it matched the predictions of general relativity with remarkable accuracy. A similar image of Sagittarius, a star the black hole at the center of the Milky Way, was released in 2022, further demonstrating that black holes are real observable objects. The detection of gravitational waves from merging black holes beginning in 2015 has opened yet another window into the study of these extreme objects. When two black holes spiral together and merge, they produce ripples in space-time that propagate outward at the speed of light. These gravitational waves carry information about the masses and spins of the merging black holes and about the properties of space-time in regions of extreme curvature. The observation of gravitational waves has confirmed predictions of general relativity and the strong field regime, and has provided new insights into the population and behavior of black holes throughout the universe. Black holes represent the ultimate test of general relativity and the limits of current understanding. They are regions where gravity overwhelms all other forces, where space-time is curved to an extreme degree, and where the classical equations of physics encounter singularities that signal the need for new ideas. Despite decades of study, many questions about black holes remain unanswered. What happens at the singularity? How does quantum mechanics modify the structure of a black hole? Can information truly be lost, or is it preserved in some form? These questions lie at the frontier of theoretical physics, and they connect gravity to the deepest mysteries of quantum mechanics and the nature of reality. The focus will shift to the profound challenges of reconciling gravity with quantum physics, and why the two pillars of modern physics have so far resisted unification. General relativity and quantum mechanics are fundamentally incompatible, and that attempts to quantize gravity using standard methods lead to mathematical problems that have resisted solution for nearly a century. One of the key ideas in the effort to reconcile these two theories is the concept of the graviton, which would be the quantum particle associated with the gravitational field, just as the photon is the quantum of the electromagnetic field. If gravity is indeed a quantum phenomenon, like the other fundamental interactions, then gravitational waves should be made up of countless individual gravitons traveling through space at the speed of light. Detecting these particles would provide direct evidence that gravity operates at the quantum level, but so far no graviton has ever been observed, and there are profound reasons to believe that detecting one may be impossible with any technology humanity could conceivably build. The graviton is a hypothetical particle predicted by attempts to create a quantum theory of gravity. According to these theoretical frameworks, a graviton would have zero mass and would travel at the speed of light, just like a photon. It would carry 2 units of spin, which is a quantum mechanical property related to angular momentum. This spin-to nature is a consequence of that gravity is described by a tensor field in general relativity, whereas electromagnetism is described by a vector field and corresponds to spin 1 photons. The mathematical structure of the theory determines these properties and distinguishes the graviton from other force-carrying particles, such as photons, gluons, and the W and Z bosons. If gravitons exist, then every gravitational interaction should involve the exchange of these particles. When 2 masses attract each other, the attraction would be mediated by gravitons passing between them in much the same way that the electromagnetic force between 2 charged particles is mediated by photons. Gravitational waves, which are ripples in spacetime produced by accelerating masses, would consist of streams of coherent gravitons moving outward from the source. The detection of gravitational waves by instruments such as the laser interferometer, Gravitational Wave Observatory known as LIGO in 2015, provided indirect evidence that gravitational radiation behaves in ways consistent with the existence of gravitons, but it did not constitute a direct detection of individual particles. The reason that individual gravitons have not been detected is that gravity is extraordinarily weak compared to the other forces. A single graviton carries an incredibly tiny amount of energy, far too small to be measured by any known detector. To put this in perspective, consider the energy required to lift a small object, such as a book, against Earth gravity. That energy corresponds to an enormous number of gravitons, on the order of 10 to the power of 40 or more. Detecting a single graviton would require an instrument sensitive enough to register the minuscule disturbance caused by 1 quantum of gravitational interaction, but the background noise from all other sources would completely overwhelm such a signal. Even the most sensitive gravitational wave detectors currently in operation can only detect the collective effect of vast numbers of gravitons arriving coherently as part of a classical gravitational wave. Some physicists have explored whether it might ever be possible to build a detector capable of sensing individual gravitons. The conclusion is that such a detector would need to be so massive and so sensitive that it would collapse into a black hole under its own gravity before it could register a signal. This fundamental limit arises from the interplay between quantum mechanics and general relativity, and it suggests that the direct detection of gravitons may be physically impossible. This does not mean that gravitons do not exist, but rather that they may remain forever beyond the reach of experimental observation. If this is the case, then evidence for the quantum nature of gravity must come from indirect means such as theoretical consistency, experimental tests of quantum effects in weak gravitational fields, or observations of phenomena that can only be explained by quantum gravity. Despite the lack of direct evidence, the graviton plays an important role in theoretical physics. It provides a way to think about gravity in quantum mechanical terms, and it serves as a guide for constructing candidate theories of quantum gravity. In many approaches to quantum gravity, including string theory, the graviton emerges naturally as one of the fundamental excitations of the underlying structure. String theory, for example, posits that all particles are not point-like objects, but tiny vibrating strings, and the different vibrational modes of these strings correspond to different particles. One particular mode of vibration corresponds to a massless spin, two-particle which is identified as the graviton. That string theory predicts the existence of the graviton is often cited as one of its appealing features because it suggests that the theory naturally incorporates gravity at the quantum level. However, string theory and other approaches to quantum gravity remain speculative because they have not yet made predictions that can be tested experimentally. The energy scales at which quantum gravitational effects become important are thought to be close to the Planck energy, which is about 10 to the power of 19 giga-electron volts. This is far beyond the reach of any particle accelerator that has been built or is likely to be built in the foreseeable future. The Large Hadron Collider, which is currently the most powerful accelerator in the world, reaches energies of around 10 to the power of 4 giga-electron volts, which is about 10,000 million electron volts, 15 orders of magnitude lower than the Planck energy. This enormous gap means that direct experimental tests of quantum gravity are not currently feasible. Some theorists have proposed that indirect signatures of quantum gravity might be detectable in astrophysical observations. For example, quantum fluctuations in spacetime at the Planck scale could in principle leave imprints on the cosmic microwave background radiation, which is the afterglow of the Big Bang. These imprints might appear as tiny irregularities in the temperature or polarization of the radiation. Similarly, quantum gravitational effects might alter the propagation of light over cosmological distances, causing subtle changes in the spectra of distant objects. So far, no such effects have been observed, but searches continue, and future experiments with greater sensitivity may provide clues. Another potential avenue for testing quantum gravity involves the study of black holes. Black holes present extreme conditions where both gravity and quantum mechanics should be important. The thermodynamics of black holes, which was developed by physicists including Stephen Hawking and Jacob Bekenstein in the 1970s, suggests that black holes have entropy and emit thermal radiation. This radiation, known as Hawking radiation, arises from quantum effects near the event horizon, and it implies that black holes are not entirely black, but slowly evaporate over time by emitting particles. The existence of Hawking radiation is a prediction that combines quantum mechanics and general relativity, and if it could be observed, it would provide strong evidence for the quantum nature of gravity. However, Hawking radiation is expected to be extremely faint, especially for large black holes, and detecting it from astrophysical black holes is far beyond current technological capabilities. The temperature of the radiation is inversely proportional to the mass of the black hole, which means that stellar mass and supermassive black holes emit radiation at temperatures far below the cosmic microwave background and are therefore effectively invisible. only extremely small primordial black holes, if they exist, would emit detectable radiation, but no such black holes have been found. Nevertheless, the theoretical framework of black hole thermodynamics has had a profound impact on the understanding of quantum gravity, and it has led to important insights about the nature of information and entropy in the universe. The search for the graviton and the effort to develop a quantum theory of gravity are closely linked to broader questions about the unification of the fundamental forces. In the 20th century, physicists achieved remarkable success in unifying the electromagnetic and weak nuclear forces into a single electroweak theory. There are also strong hints that the electroweak and strong nuclear forces might be unified at even higher energies in what is called a grand unified theory. Gravity, however, stands apart. It has not been incorporated into these unification schemes, and its inclusion remains one of the ultimate goals of theoretical physics. A successful theory of quantum gravity would not only explain the behavior of space-time at the smallest scales, but might also reveal deep connections between gravity and the other forces. Some researchers believe that the difficulty in quantizing gravity is a sign that a radical rethinking of fundamental concepts is needed. Perhaps space-time itself is not fundamental, but emerges from some deeper underlying structure. Perhaps the familiar notions of particles and fields are approximations that break down at the Planck scale. These ideas have led to a variety of speculative proposals, including the holographic principle, which suggests that the information content of a region of space can be encoded on its boundary, and the idea that space-time might be a quantum error correcting code. These proposals are highly abstract and far from being fully developed, but they represent attempts to go beyond the standard frameworks and find new ways to understand the relationship between quantum mechanics and gravity. In summary, the graviton is a hypothetical particle that would mediate the gravitational interaction in a quantum theory of gravity. It is predicted to be massless with spin 2 and to travel at the speed of light. However, no graviton has ever been directly observed, and the weakness of gravity makes such detection extraordinarily difficult, if not impossible. Theoretical frameworks such as string theory predict the existence of the graviton and attempt to describe gravity in quantum mechanical terms, but these theories have not yet been experimentally verified. Indirect evidence for quantum gravitational effects might come from observations of black holes, the cosmic microwave background, or other astrophysical phenomena, but so far no conclusive evidence has been found. The search for the graviton is part of the broader effort to reconcile general relativity with quantum mechanics and to develop a complete theory of quantum gravity. The discussion will turn to some of the leading candidate theories for quantum gravity, including string theory and loop quantum gravity, and examine how these approaches attempt to solve the problem of unifying the two great pillars of modern physics. Alternative and speculative approaches to understanding gravity, including Jonathan Oppenheim's proposal for a hybrid theory, in which space-time remains classical while matter is quantum, and the idea that space-time itself might be emergent rather than fundamental. These unconventional ideas reflect the deep uncertainty that persists in theoretical physics, and the recognition that the problem of reconciling gravity with quantum mechanics may require revolutionary new concepts. After journeying through 14 parts examining gravity from its apparent simplicity to its most profound mysteries, it is time to step back and acknowledge a striking truth. Despite centuries of study and remarkable progress, humanity still knows astonishingly little about what gravity truly is at the most fundamental level. Gravity is the most familiar of all the forces. Every person feels it every moment of every day. It holds people to the ground, keeps the atmosphere in place, and governs the motion of the moon around the Earth and the Earth around the Sun. Gravity shapes the structure of galaxies and determines the fate of the universe itself. Yet this ubiquitous interaction remains the least understood of the four fundamental forces. Electromagnetism, the strong nuclear force, and the weak nuclear force have all been successfully incorporated into the quantum framework of the standard model of particle physics. Gravity alone stands apart, resisting every attempt to fit it into the same mathematical language. The journey through this script began with the observation that gravity is often misunderstood and oversimplified. The story of Newton and the falling apple captures an important insight, but it hides the depth of the mystery. Gravity is not just a force that pulls objects together, it is a manifestation of the curvature of space-time itself. It affects not only the motion of matter, but also the flow of time. Clocks run slower in stronger gravitational fields, and this effect has been confirmed by experiments with atomic clocks on airplanes and satellites. The global positioning system relies on corrections for time dilation to provide accurate navigation, and every use of a GPS device is a confirmation of Einstein's general theory of relativity. Yet even general relativity, which had passed every experimental test with extraordinary precision, does not answer the most fundamental questions. What is space-time made of? Why does mass curve space-time in the way that it does? What happens at the center of a black hole where the curvature becomes infinite and the equations break down? What occurred at the very beginning of the universe during the Big Bang? These questions cannot be answered within the framework of general relativity alone, because the theory encounters singularities where the predictions become meaningless. Singularities are signals that the theory is incomplete and that a deeper understanding is needed. That deeper understanding must come from a theory of quantum gravity, which would combine the principles of general relativity with those of quantum mechanics. However, constructing such a theory has proven to be extraordinarily difficult. The standard techniques of quantum field theory, which work so well for the other forces, led to mathematical inconsistencies when applied to gravity. The hypothetical particle that would mediate gravity in a quantum theory, the graviton, has never been observed and may be undetectable in principle due to the extreme weakness of the gravitational interaction. String theory and loop quantum gravity offer promising frameworks for quantum gravity, but neither has yet produced testable predictions that could be confirmed by experiments. The challenges run deeper than just technical difficulties. Quantum mechanics and general relativity are based on fundamentally different assumptions about the nature of reality. Quantum mechanics describes a world of probabilities, superpositions, and uncertainties, where particles do not have definite properties until they are measured. General relativity describes a world of smooth, continuous geometry, where space-time is a deterministic structure shaped by the distribution of mass and energy. Bringing these two worldviews together requires reconciling not just equations, but entire conceptual frameworks. It may require abandoning some of the assumptions that have guided physics for the past century. This conceptual challenge is reflected in the diversity of approaches being pursued. String theory suggests that the fundamental building blocks of nature are not particles, but tiny vibrating strings, and that space-time has more dimensions than the four that are observed. Loop quantum gravity proposes that space-time itself is discrete and granular at the smallest scales. Hybrid theories suggest that gravity might remain classical while matter is quantum. Emergent space-time scenarios propose that space and time are not fundamental, but arise from deeper underlying structures. Each of these ideas represents a different way of thinking about the universe, and each offers different insights into the nature of gravity. The lack of experimental guidance is one of the most frustrating aspects of the search for quantum gravity. The energy scales at which quantum gravitational effects are expected to become important are far beyond the reach of any experiment that has been or could be performed with foreseeable technology. The Planck energy, where quantum gravity should dominate, is about 10 to the power of 19 giga-electron volts, which is roughly a quadrillion times higher than the energies accessible at the Large Hadron Collider. Without data to constrain the theories, physicists must rely on mathematical consistency, aesthetic principles, and indirect arguments. This is uncharted territory for physics, which has traditionally been guided by close interaction between theory and experiment. Despite these obstacles, there are reasons to believe that progress is possible. Observations of gravitational waves are providing new ways to test general relativity in strong field regimes, and future detectors may reveal subtle effects that could hint at quantum gravitational phenomena. Studies of the cosmic microwave background are probing the very early universe, where quantum gravity may have left detectable imprints. Advances in quantum information theory and the discovery of deep connections between entanglement and space-time geometry are opening new avenues for understanding how quantum mechanics and gravity might fit together. The field is alive with new ideas, and there is a sense that important discoveries may lie ahead. Yet it is also important to recognize the limits of current knowledge. Gravity confuses even the most accomplished physicists. It is the most well-known force, yet the least understood. It shapes the universe on the largest scales, but disappears on the smallest. It is described by one of the most elegant theories ever constructed, general relativity, yet that theory cannot be reconciled with quantum mechanics, which is equally elegant and equally successful in its own domain. Gravity bends, light slows time, and creates black holes, where the known laws of physics break down. It is simultaneously the most obvious and the most mysterious feature of the cosmos. This mystery is not a failure of science, but a testament to the depth and richness of the natural world. That gravity remains enigmatic after centuries of study shows that the universe is far stranger and more complex than everyday experience suggests. It reveals that there are still profound questions to be answered and fundamental truths to be discovered. The search for a complete understanding of gravity is one of the great intellectual adventures of the modern age, and it is an adventure that is far from over. The story told across these 15 parts has moved from the familiar to the exotic, from falling apples to black holes, from everyday experience to the Planck scale. It has shown that gravity is weak yet dominant, local yet infinite, gentle yet relentless. It has revealed that time is not absolute but flexible, shaped by mass and motion. It has demonstrated that space and time are not separate but woven into a single fabric that can be curved, stretched, and rippled. It has explored the frontiers of theoretical physics, where the quest to unify gravity with quantum mechanics pushes the boundaries of human understanding. In the end, the most important lesson is one of humility. For all the progress that has been made, for all the experiments that have confirmed Einstein predictions, and for all the sophisticated theories that have been developed, gravity remains fundamentally mysterious. The question of what it really is at the deepest level has not been answered. The quest to understand gravity is not just about solving equations or building detectors. It is about comprehending the nature of reality itself. It is about understanding how the universe works at the most fundamental level and what the rules are that govern everything from the smallest particles to the largest structures. Gravity is not just a force or a curvature or a particle. It is all of these, and perhaps something more. It is a window into the deepest secrets of the cosmos, and a reminder that the universe is full of wonders that have yet to be uncovered. The journey to understand gravity has led through centuries of discoveries, and it has involved some of the greatest minds in history. Yet the journey is not complete. Many questions remain unanswered, and many mysteries remain unsolved. The universe still hides huge secrets, and humanity has only just begun to understand this most fundamental and most puzzling of all interactions. The next breakthrough may come from an unexpected direction, and it may require ideas that have not yet been imagined. Until then, gravity remains one of the greatest unsolved mysteries in science, and the adventure of exploring it continues.